the neutrino is the closest thing to nothing we can imagine. It has zero size, zero charge, mass very close to zero, and it interacts so weakly with everything. But somehow or other, the neutrino isn't nothing. It might be the key to the universe.
For astrophysicists, the universe is one huge laboratory in which most things still have to be discovered. The matter of which the stars, planets, interstellar gas clouds, and humans are composed only accounts for a mere 5% of the universe's mass. The rest is an enormous, unsolved puzzle. The human eye is woefully inadequate to see everything in the universe. Astrophysicists are looking for apparatus that will help them investigate the tremendous events in the cosmos, for which they have any number of theories, but precious little concrete information. They are not simply neutrinos, in our case, neutrinos with particularly high energy. They are neutrinos conveying a message. They're ambassadors. They tell us something about the object from which they come to us. This object must be something in which incredibly high energy is released, many times higher than that in the Sun. We're looking, for instance, at neutrinos from the destructive processes of dark matter. Possibly these neutrinos will give us an indication of what dark matter is. Ten years ago, an international team of scientists started to build a gigantic detector to catch these high-energy neutrinos in one of the most remote places in the world, the South Pole. Deep in the ice, the scientists are looking for the flashes of light that a neutrino releases when it collides with matter. With a mobile drilling station, the research team has melted countless holes kilometers deep into the Antarctic ice cap. Here the ice is so deep and pure that the detector, which measures a cubic kilometer, has sufficient space and ideal conditions. A hot water drill, which draws down its own weight as it melts the ice, has prepared the way for photosensors in the crystal clear ice. The upper layer of the ice sheet consists of snow. The snowflakes change as they are pressed down deeper and deeper over many thousands of years, from graceful ice crystals to compact, transparent ice. The meter-high flakes are transformed into firn, a layer of compacting ice. More and more snow presses the air out of the firn. It becomes denser and even more compact, until finally it is a body of ice almost free of air. The scientists have introduced photosensors the size of basketballs into the ice, on separate strings like threaded beads, up to a depth of 2.5 kilometers. Within a single day, the drill hole freezes closed. When the work's completed, a cubic kilometer of ice is full of sensors.
Yeah, there we go.
The gigantic detector is now ready. Deep within the crystal clear ice, where it is pitch dark, thousands of highly sensitive photosensors wait for minimal but far-reaching traces of light. And these traces only occur when a neutrino collides with an ice atom. In 2013, scientists first discovered conspicuous traces of light in the IceCube detector.
Das Neutrino selbst kann man nicht fangen, nicht? Das Neutrino.
We can't catch the neutrino itself. It interacts with matter very rarely. A reaction of that kind only occurs in our detector if we're very lucky. Then it reacts with an ice atom and releases secondary particles, which move hundreds of meters through the ice. Behind them, they draw a ball of light, which is called Cherenkov light, after the man who discovered it. And it's this that we identify with the IceCube. We have succeeded in identifying high-energy neutrinos for the first time. Ernie and Bert. They had such high energy that it was extremely unlikely that they were created in the Earth's atmosphere. These neutrinos must have come from outside our solar system. When a cosmic neutrino, which is much smaller than the nucleus of an atom, collides with an ice atom, it leaves behind a trace of light that spreads over several hundred meters. The scientists call their discoveries Ernie and Bert. The breakthrough after decades of research. All over the world, scientists are searching for these messenger particles from the distant universe. Also on the other side of the planet, in Europe, a research institute on the French coast, southwest of Toulon, is the base for a tremendous Mediterranean project. This building was constructed in the 19th century. Now it captures the data of minuscule flashes from the sea. Here researchers are trying to decode the neutrinos' oscillations, their transformation into three so-called flavors on their flight path. Antares, the small prototype of a neutrino deep-sea detector off the coast of southern France. It's already sending data. It's still a prototype. Within a few decades, a cubic kilometer large detector field is planned. KM3 net.
Each box corresponds to one of the detection strings. Each cross represents the height and the time of the photon that was detected. So on these displays, we can see a kind of time history of the counting rates on the optical modules. The main source of light that we detect is from the natural radioactivity of the salt. The potassium-40 isotope of the salt emits a little beta particle which emits light. So most of this light is just due to this natural radioactivity in the sea. But every now and then we may get a fluctuation or a spike in the time chart, and that is associated with bioluminescence activity. In the sea, the organisms have evolved to emit their own light, bioluminescence, and if one of those organisms comes close to the telescope, it could even bump into the telescope and go ouch and make a flash of light in reaction.
Nous avons étudié les corrélations entre la...
The aim of our research into bioluminescence is the connection between bioluminescence values and the physical parameters of the Mediterranean, which is a small ocean. Especially the temperature and the salt content have a great effect on the behavior, the movement patterns, the mixing ratio and currents of the water masses. We want to understand these dependencies better.
La direction du courant.
KM3 net will be a multifunctional measuring instrument in the sea, supplying biologists, geologists and physicists with data. Apart from neutrinos, the scientists can already detect specific species of whales and dolphins in the Mediterranean.
Donc là, vous avez sur cette bande...
Here's the expired time, and in the verticals I can read the sound frequencies.
Et donc, chaque fois qu'il y a un signal...
Each time a signal is detected, I see a color code and hear a click. So I can hear short broadband signals, clicks, in real time, a few milliseconds after the dolphins or whales, especially toothed whales and sperm whales transmit them.
20 years ago, we started the development of the Antares telescope. It took some while to learn the tricks of the trade of how to build very large infrastructures, very deep in the sea. Antares was in fact 12 detection strings, but our project that we're building now, KM3net, will be many hundreds of strings. So this will dramatically increase the chances and essentially guarantee that we will be able to have unambiguous detection of cosmic neutrinos.
Neutrinos are all around us, but we have no idea where they come from. These elementary particles that have 1,000 times more energy than those from the world's largest particle accelerator, the Large Hadron Collider in Geneva. The most trivial neutrino source is humans. All of us have potassium in our bodies. A radioactive isotope of potassium, potassium-40, undergoes beta decay, which produces neutrinos. Our bodies transmit between 4,000 and 5,000 neutrinos per second. Particle and astrophysicists, however, are much more interested in solar neutrinos, which we've already identified. In fact, on every square centimeter, say on every fingernail, 60 billion solar neutrinos arrive every second, and they fly through us, irrespective of where we're standing, facing away from the sun or towards it. Some 60 billion neutrinos race through every square centimeter all over the Earth every second. The sun burns hydrogen in its core at a temperature of 15 million degrees Celsius. Light particles, and also neutrinos, are emitted. The sunlight we see has required thousands of years to pass through the sun's successive layers. Only the neutrinos leave the core immediately. Just 8 minutes after their creation, they reach the Earth. But these are low-energy neutrinos. We are looking for neutrinos that come to us from entirely different processes, not from nuclear reactions as in the Sun, but from massive accelerating processes, cosmic accelerators similar to our Geneva accelerator, LHC, but accelerated many times faster, so with much higher energy. That's why we're hoping for information from the cosmic neutrinos, which we can't derive from any other source. Neutrinos are a small part of the cosmic radiation that constantly rains down on the Earth's atmosphere. We've known about this radiation for more than 100 years. But where and how these particles originate is still a puzzle. All we know is that it's a highly energized particle radiation comprising mainly protons and atomic nuclei. The charged cosmic particles are diverted into magnetic fields. That's to say, they meander through space. And though they come from a particular direction, they get so distracted that they arrive on Earth from the opposite direction. So we can't trace their route or their source. Their path is distorted. So we need neutral particles which don't get distracted. That's why neutrinos are ideal for us, because they are neutral, because they come from compact objects from which light can't escape, and because they can simply fly through matter. They're distracted neither by stars nor specks of dust. Here in the Mediterranean, the KM3net detector is being constructed. It will be built in 3 sections, one of them off the coast of Italy, another off the coast of France, and the third off the coast of Greece. They will be 4 kilometers underwater and digitally linked to form a giant detector. In its maximum extension, KM3net will be 10 cubic kilometers large. Whereas ice is the detecting medium of IceCube at the South Pole, the detecting medium here will be water. But deep-sea conditions make entirely different demands on the planning and construction of the detector. To read the data from the water, the scientists are installing an infrastructure on the seabed, which will gather the data, bundle it, and transfer it via special deep-sea cables to the analysis stations on the coast. With an instrument the engineers call WORM, which uses extreme water pressure, they dig a deep channel into the upper layers of shell and stones until they strike a harder layer of rock. On this solid foundation, an accompanying diver lays the cable and immediately covers it with shell limestone and mud for protection.
To power the detector and to transfer the data from the detector to the shore, we have this submarine cable, which is a telecommunications cable. Then to actually transfer the data, we use these optical fibers. So in the KU3net cable, we have 36 optical fibers. To protect the cable from the possibility of boat anchors damaging the cable, we have this extra armor plating around the cable, 2 layers, an inner layer here and a thicker outer layer here. Further out to shore, it's a single armor, and then when it's in deep water, below 1,000 meters, there is no protection. It's just the polyethylene cable.
Zeuthen, south of Berlin, is the location of one of the leading centers of neutrino research, the German electron synchrotron, DESY. This is where a team of particle physicists developed the sensors from which IceCube at the South Pole is constructed.
In
this glass sphere, you see a photomagnifying tube. It's held in this optical module and is very light sensitive. As soon as a single photon falls on this side, it produces a tiny electrical current. The electronic module here in the upper part of the sensor emits the current. This is the glass sphere that protects the sensor from the enormous pressure of the deep ice. And inside we have the electronic module, which amplifies the tiny electrical current, digitalizes it, and then sends a signal to the IceCube laboratory on the surface. Thousands of synchronized sensors measure the precise time and strength of the light event and communicate the data. In their laboratory, the researchers are already working on the next generations of light sensors. They should be cheaper, simpler, and more efficient. One idea is to conduct the Cherenkov light through coated tubes. The scientists are looking for ultraviolet light. The postdoctoral student, Jakob van Santen, is getting ready for his first assignment at the South Pole. You have to be really fit to fly to the South Pole. I have to get a thorough medical checkup. And when I get the okay, I'll set off for Christchurch, New Zealand. I'll have to wait there for quite a while until the weather conditions are right. Then I'll fly 8 hours to the Antarctic coast, and then 1.5 hours to the South Pole.
Bis man dann zum Südpol fliegen kann. Das dauert dann nur 1,5 Stunden.
I've been working on the IceCube project for a long time, but I've never seen my experiment. I'm really looking forward to that. And it's great to be traveling to a place which only a few people have visited. The journey to the South Pole is an adventure for the young scientist. The Antarctic is larger than Europe. Its surface includes land, continental ice, and a gigantic ice sheet. 98% of the region is covered in snow and ice. In summer, the ice surrounding the southernmost continent melts to 3 million square kilometers, 1/6 of its winter surface. Because of the altitude of its terrain, the extremely low temperatures and low precipitation, the Antarctic is also one of the driest regions. In fact, the world's largest desert. It's many days before van Santen finally reaches the Antarctic. He flies the last leg of his journey to the South Pole in a US Army supply plane. He lands on the ice sheet at an altitude of 3,000 meters. It's summer here, and it's high season. Researchers come to the South Pole in summer. Only a skeleton crew remains during the dark, cold winter to keep the detector running. Everyone who comes here is excited to reach the South Pole, but some suffer from altitude sickness from the moment they arrive. It takes a few days to acclimatize. For the researchers, the new Amundsen-Scott South Pole Station is an oasis in the middle of the ice desert. It guarantees their survival. The station can accommodate several hundred people. Everything here is simple and practical. But Scott and Amundsen, who were the first to reach the South Pole more than 100 years ago, would be astonished by the comfort and technology. This is an astrophysics hotspot. Deep in the eternal ice, the researchers are discovering cosmic light signals. IceCube is searching for neutrinos that have flown through the Earth, ones that entered the northern hemisphere. Ones that entered the southern hemisphere are looked for in the Mediterranean, for only neutrinos can fly through the Earth. The KM3 net detector will also search for particles that have traveled through the Earth. Since the Mediterranean is more than 5,000 meters deep, Catania, on the east coast of Sicily, is an ideal spot for a research station. A team of European scientists is here to install the first section of the detector on the seabed. Physicists have adapted the structure of the photosensors to deep-sea conditions. Water pressure, salt, and sea currents are formidable challenges. The sensitive electronic module has to be protected to make the most precise measurements at any moment. The biggest problem is that these objects have to be placed at a depth of 4,000 meters in the sea. Everything has to be correct because it's very difficult to pull them back up from the sea to repair them. So everything has to work perfectly before the mission begins. It takes a long time to produce and test each optical module before it can be released and deployed in the sea. This kind of physics, the astrophysics of neutrinos, is a completely new branch of physics. It's absolutely innovative. With these neutrinos, we'll make a new map of the heavens. The physicists register the sensors to sort the data they will receive out of the depths. In the Scott Amundsen station at the South Pole, Jakob van Santen is now feeling at home. He can reach the IceCube on foot. It's a beautiful day, almost no wind, summer temperatures of minus 30 degrees Celsius, glorious sunshine. The station is about 500 meters behind me, and in front of me, it's only about 500 meters to the IceCube laboratory. I'm going there now to see how our detector is doing. These rods and flags are the only parts of the IceCube you can see on the surface. Most of the detector lies 1.5 kilometers under my feet. IceCube is a superb neutrino detector, a gigantic high-tech IceCube. buried 2.5 kilometers deep in the eternal ice at the South Pole. It's dark down there, and the ice is extremely pure. Light is able to illuminate IceCube without distractions. The eyes of the telescope watch for the tiniest flashes of light. 5,200 photosensors register the weak light of the particle traces, which can travel many hundreds of meters through the ice. When light signals are discovered, the sensors transform them into electrical signals and conduct these along the steel cables to the surface, to IceCube. Into the brain of the telescope.
Hello.
The first computer center has already been installed in IceCube. It registers all the data from the ice, filters it roughly, and then sends it to research centers all over the world. Data from each of the more than 5,000 sensors in the ice is gathered here. This is the detector's control center. It receives its power from here. Thousands of meters of cable and cupboards full of computers. Day and night, a small team of scientists monitors the electronics in the IceCube.
I'm hired to keep the detector running, so whatever happens, I have to solve it. This makes me happy because these lights you see in the back, if you see green, yellow, red, then IceCube is taking data. Yeah. It's beautiful, eh?
Yeah.
It's very photogenic too. I've been taking a lot of pictures here of the cables and
To keep the detector running, some of the scientists remain on the ice during the winter. Then it is minus 70 degrees Celsius here, and always night. The sun stays below the horizon. Only the moon follows its regular course. This is perfect for viewing the iridescent polar lights, ionizing solar wind that meets the Earth's atmosphere and is diverted to the poles. But now, during summer at the South Pole, when it's winter in Europe, the sun never sets. It circles the pole at a fixed distance to the horizon. The rhythm of day and night is suspended. The day has 24 hours of sunlight, and you can't orientate yourself on the sun's position. It's just a single day that never seems to end. Jacob van Santen's trip to the high-tech detector IceCube in the Antarctic ice ends after 10 solar days. A large computer farm in the grounds of Daisy near Berlin is both a modern memory and a gigantic computer. The data from IceCube at the South Pole is transmitted here by satellite. Disruptive signals and other influences are filtered out. We do this for billions of events in IceCube and fish out the rare events of cosmic neutrinos. Data analysis is a very complicated process. Where did the neutrino interaction take place in the detector? How much energy did the event have? And what direction did it come from? It's like looking for the needle in a gigantic haystack, looking for neutrinos that have so much energy that they could have originated outside our galaxy. The scientists continue filtering the countless events in the ice until they come across the decisive light signals.
Also ja, das sind jetzt...
This is the raw data. We see the whole detector, but not in real time, much slower. I've only read out 1 second here.
Eine Sekunde ausgelesen.
But that's 1,000 times slower than in real time. Switch to real time, please. Then the clip lasts 1 second and flashes madly.
Blinkt gewaltig.
Filtering the data more and more, the researchers arrive at their goal. The strongest light trails in the ice have a diameter of up to 600 meters. A 600-meter-long light trail left by a particle so small that it's invisible.
Dann sieht man wirklich nur
Now we really only see a trace.
da, wo wirklich viel Licht war.
Here the trace clearly passes through the detector. A myon producing Cherenkov radiation, no question.
Hier sieht man es ganz klar.
Ernie and Bert are no longer alone. Since discovering them, researchers have been able to identify other cosmic neutrinos. The one with the most energy to date they have named Big Bird.
Also die große Hoffnung.
We are hoping to be able to identify the sources of these high-energy neutrinos as soon as possible. The big question is, how is this cosmic radiation produced? How is it accelerated? What are the cosmic accelerators that must exist? I hope I don't have to spend the rest of my life researching these questions, but I definitely want answers to them. The sooner the better. Downtown Berlin. Location of the Zeiss Planetarium. This is one of Europe's largest planetariums, and the city administration is making it one of the most modern. The news of the extra-galactic neutrinos fascinates the director. To show them in the planetarium dome at the reopening would be sensational. Planetarium director Tim Florian Horn is a specialist in visualizing cosmic phenomena. Using the most modern projection techniques, he wants to make the latest developments and discoveries intelligible to his visitors. The Berlin Planetarium is a modern theater of science.
Immer wenn was Neues entdeckt wird.
Whenever anything new is discovered, we want to talk about it and show it. We can help people understand neutrinos best if we can show their path through the cosmos. That works very well in the planetarium because our audience gets an idea of the enormous distances in the universe.
Entfernungen eigentlich zwischen den Orten im Weltall sein können. Allein im Sonnensystem wäre man in Echtzeit.
In real time, of course, they'd need months to fly through the solar system, so we have to suspend some natural laws. We fly faster than the speed of light to a place where, in reality, we would be destroyed by radiation. If we ventured beyond our Milky Way, we wouldn't be able to see other galaxies because our eyes weren't created for that. It's a narrow path we're treading. We want to be scientifically correct, but also intelligible for the audience. So we have to make compromises in scientific accuracy in the interests of intelligibility. Basically, we're a translation office for science.
Im Grunde sind wir ein Übersetzungsbüro für die Wissenschaft.
To visualize the newly discovered neutrinos, Horn meets up with the neutrino researcher Christian Spiering and a visual artist in the animation department at the Potsdam-Babelsberg Film Studios. Their aim is to bring a cosmic neutrino to the screen, to make the discovery of an invisible object comprehensible to a wide audience. None of them knows what a neutrino really looks like.
Was zeigen wir?
If we want to represent neutrinos, what can we show? How do we conceive of a neutrino? How might it move through the universe?
Also ich
I can only imagine how a neutrino moves, and I imagine something like the trail of a jet plane without seeing the plane itself. I'm really only interested in how and why it flies its path. Or I simply imagine a neutrino as the Greek letter ni. That's enough for me. Basically, I only see a formula. On this issue, I ask myself, where do they come from? How do they move? How do we show that?
Ich bin das Neutrino.
I'll make a suggestion. I'm the neutrino. I fly through the room. Yes, a subjective flight might be the answer. I race through the universe, various galaxies approach, I leave them behind, then comes empty space, just empty space. Then at some point, our galaxy turns up, and then a blue sphere in the distance. And that's the Earth. So far, Spiering has only thought of neutrinos as particles without a shape. The visual artist presents him with various ideas. That's more like an atomic model, certainly not a neutrino in my understanding. For me, a neutrino is more like a point, without structure, very tiny. Okay, next suggestion, a model that shines and appears to be intangible with an external oscillation. That looks more like friendly elves oscillating around a green sphere. With green vibrating bands, I understand. This one's interesting, out of focus. Makes me think immediately of solar eruptions. Of course, we also have the problem that certain images are already familiar. This one probably looks like Star Trek. It wafts around indecisively in space. And it looks very wound up. Yes, very excited neutrino. Previously, I saw something interesting in the computer preview, a sharply defined sphere, rather like a billiard ball. If those edges could fray out or blur, I think we would be closer to the ghostly particle. For me, it's just a bit too big in relation to the screen. No problem. Yes, like that. Let's try that. In the Center for Particle Physics in Marseille, the French research team is getting ready to install the first KM3 net detector chain.
These are the eyes of the telescope, and the photomultipliers are very, very sensitive to light. They can catch just one single photon. The human eye actually requires about 7 photons before you can trigger that you've detected something, whereas these are much more sensitive than the human eye. And we need to measure the position where the photon arrives on the detector with a few centimeter precision. But of course, in the bottom of the sea, we have the sea currents, and in fact, everything is slightly moving. And so inside the optical module, we have some very precise compasses which measure the rotation of the sphere and its inclination in all directions.
As soon as a neutrino hits the nucleus of an atom in the detector, it races on as a myon. The myon emits light and activates the individual senses on its flight path. From the direction of the flight path, the researchers can reconstruct the position of its source.
The amount of light that we detect in the telescope actually depends on the energy of the neutrino. So if a low energy neutrino was to interact, there wouldn't be very much light, whereas when it's a very high energy event, the whole detector will be lit up like a Christmas tree.
KM3 net will be a powerful deep-sea detector, the counterpart of IceCube in the northern hemisphere. Each detector string is 800 meters long and carries 18 sensors the size of basketballs.
So if you were able to walk around on the seabed amongst the forest of detectors, I think it would be quite an impressive sight to see.
The telescope is not rigid. It floats on the water current. So every sensor has to continuously redefine its position. That's the only way the researchers can determine the direction of the neutrinos. Back to the animation studio. From the planetarium, Tim Florian Horn has brought a software program that can simulate the known universe. In these vast spaces, the team tries to create a dead-straight path for the neutrino, from its source to the Earth.
A
graphic card or a computer system can't represent these large scales sensibly. We have to be a bit cunning. We'll compress the various coordination systems and we'll fly much faster than light. When we're crossing matter, whether it's the Earth or an asteroid, it would be good to try and zoom in on the atomic level. I mean, the level where, as a neutrino, I only see an atom in front of me, the nucleus in the center with a few electrons circling it. Because at the end of the day, an atom is an empty system through which the neutrino flies completely unhindered. Basically, the whole of Earth consists of these empty systems, and that's why it's porous for the uninvited neutrinos. The atomic level should show why the neutrino can fly unhindered through walls and whole planets, a flight through the void. In Marseille, the researchers are preparing to transport a detector string. Here we have the structure we use to install KM3 net at a depth of 4 kilometers in the Mediterranean. The KM3 net sensor lines stretch hundreds of meters high vertically from the seabed. 800 meters when set for the higher energies and 200 meters high for our setup here in France. But before installing these vertical structures, we first wind the cable, which is a flexible cable, onto this spherical structure.
On enroule d'abord la ligne sur cette structure qui est sphérique.
Every action is carefully planned and tested several times. The scientists roll the string with the sensor spheres into a big ball. They have developed a special anchor to secure it on the seabed. The final step in the construction hall is to load the rolled-up string onto the yellow anchor. The first sensor chain is ready for shipping. Together with the anchor, it's loaded and sent off. A research vessel transports it 40 kilometers offshore. Tonight, the first KM3 net string is due to reach the bottom of the Mediterranean at a depth of 3,500 meters. Slowly, at a speed of 12 meters per minute, the anchor and sensors sink onto the seabed. They are accompanied by submersible robots steered by engineers on board the research vessel. 4.5 hours later, the load reaches the bottom. Robotic arms attach cables linking the anchor with the deep-sea infrastructure that transmits energy and information to the coastal station. Then a buoy hoists the frame. The sensor string unwinds vertically from the metal frame like wool from a ball and releases the individual photosensors to their specific final positions. Assembling the first detector string is successful. Many hundreds more will follow. Soon, KM3 NET will also be able to identify extra-galactic neutrinos. In the Berlin Planetarium, the researcher animation team wants to take a look at its first results. A cosmic premiere screening. Scientists view the universe as a gigantic laboratory for testing the validity of the basic laws of physics, and to investigate regions in which gravity, density, and temperature are extremely high. There where stars explode or implode and a black hole is created. A cosmic explosion in a gigantic particle accelerator a million light-years away. An enormous jet sent out by a gigantic black hole in the heart of an active galaxy. These jets can reach hundreds of thousands of light-years into intergalactic space. They accelerate the cosmic particles, thereby producing neutrinos. A neutrino flies slightly slower than the speed of light. Since it comprises only a smidgen of matter and isn't charged, other particles don't decelerate it or distract it from its flight path. So it can pass through everything without risking a collision. Atoms of which our bodies are made consist of more than 99% empty space. Between the nucleus at the center and the even tinier electrons circling it, there's a great deal of space for the neutrino, and nothing but an electrical field. But unlike most other particles, the neutrino doesn't register electrical forces. It has to collide directly with a nucleus for it to be stopped. And that occurs very, very rarely. This rare event can only be discovered with the aid of gigantic detectors. Only by chance, and with the slight risk estimated by the scientists, does a neutrino strike an atomic nucleus. Now these extra-galactic neutrinos have been identified for the first time. Ernie and Bert are the megastars of astro and particle physics. In discovering cosmic neutrinos, we have opened a new window. However, we haven't opened it fully, just a crack. We know there's something there, but we haven't mapped this new landscape yet. When we find more of these particles and trace them to definite sources, we'll be able to create a mosaic. And then we'll be able to say how these sources really function, how the wildest machines in the cosmos work. Modern physics shows that the behavior of elementary particles at the smallest level and the development of the universe as a whole are inseparably linked. With models and theories, scientists are trying to gauge and extend the boundaries of physics. Neutrinos will help to prove those theories.
Our main goal will be to discover a single point-like source of neutrinos. So that could be sources like black holes, accreting matter, collisions of black holes, or supernova explosions. To be sure that we detect such a source, we would need something like 10 neutrinos pointing from a single location in the sky. History has shown that every time you switch on a new telescope, you should not be surprised to have a surprise.
If there are highly developed civilizations, perhaps they don't want to be spied on by underdeveloped civilizations like ours. Maybe they decided not to use electromagnetic waves to communicate, but something quite different. For instance, neutrinos. Just imagine. That would mean that neutrinos are something like Morse code from extraterrestrial civilizations.
Von außerirdischen Zivilisationen in Neutrinos.